All right, we're going to start out in the first chapter with a review of exponential and logarithmic functions. And in this first section, focusing on the exponential function, differentiating them, integrating them. So our first theorem, this is stuff that we've learned in Calc 1, right? So maybe it's been a little while since we've taken Calc 1, so kind of just a refresher on this material. E to the x, you might remember, is our favorite function. It's our favorite function because it is its own derivative, and that's what we see here, right? The derivative of e to the x is e to the x. Now, if we don't just have x in the exponent, but maybe some function of x, some stuff, which we refer to as u, then it's still its own derivative, except that we have to follow up by multiplying by the derivative of the stuff. That's this du dx on the end. This is what we call the chain rule. You see the chain rule really in every derivative formula. In every theorem that tells us how to take the derivative of some stuff. We see it in the power rule. Right, so I'm sure you remember that the derivative of u to the stuff is not u to the stuff to the n power, right? So something raised to the n power, you bring the power down, and then you have that same stuff to the one less power, and then you have to multiply by the derivative of the stuff. So there's the chain rule there. In all of the derivative formulas that we'll see, you're going to see that times du dx at the end. So let's do some examples. The derivative with respect to x of e to the 2x minus 1. Okay, so in this case our stuff is 2x minus 1. So the derivative of e to the 2x minus 1 is e to the 2x minus 1. We start by repeating the function itself, and then we multiply by the derivative of 2x minus 1, which is 2. And so just simplifying this, put the coefficient in front. And there's our derivative. Let's do another one. Here we've got e to the negative 3 over x. We want to find the derivative with respect to x of this function. Well, I know the way it starts, right? It's e to some stuff, so we're going to take the derivative. The first thing we've got is e to that stuff, e to the minus 3 over x. But I know I need to multiply by the derivative of that stuff. So I'm going to do a little side work in this case. Here, u is equal to negative 3 over x. And I'm going to rewrite this to make the derivative simpler. This is minus 3x to the minus 1. So this is really a power rule. Now, if you looked at negative 3 over x and you were thinking to yourself, I can use the quotient rule to find the derivative, you're absolutely right. You can. It's just a little bit more work. So if we rewrite it this way, finding the derivative is easier because we can use the power rule. Du dx. I'm going to bring the negative 1 down, multiply it, so that's a positive 3, and then x to the minus 2. And so that's what we're going to multiply by over here when we apply the chain rule. Now what we want to do is simplify. I have all these negative exponents, so I think what I'll do is write this as a fraction. So the 3 stays on top, and I guess, I'm going to do this maybe in a couple of steps, right? So I've got this 3, e to the negative 3 over x. X to the minus 2 is a negative. But really, I think it might make sense to throw that e in the bottom anyway. I think either way would be acceptable, but if I've gone to the trouble of rewriting this with negative exponents, without negative exponents, then I will just go all the way with that. So there's our derivative. Our next example. This is going to kind of test our memory a little bit. Find any critical values and any maxima or minima for the function f of x equals x e to the x. All right. So this is going to involve the derivative, but we'll just remember that a critical value happens any place where the derivative is either 0 or undefined. So we're going to start this by finding the derivative. So f of x is equal to x times e to the x. So this is a product, and we are going to use the product rule. So my two factors, I'm going to call them u and v. So let's say here's u and here's v. These are the things, whoops, that we're multiplying together. So the product rule goes like this. I'm going to write it over here on the right side. The derivative with respect to x of u times v is equal to v times du dx plus u times dv dx. Alright, so we kind of take turns of which function we take the derivative of. We find those products and we add them together. So in this case, let's see, v is e to the x. Du dx, the derivative of x, is 1, plus u is x, and the derivative of e to the x is e to the x. I'm going to simplify this by factoring out the e to the x, and then inside we have 1 plus x. So here's our derivative. Oh, and just I'm going to make a quick notation comment here. This first line says f of x equals x e to the x. That's absolutely true. Then I just wrote an equals sign down here, which is not something I should do, because this line is equal to the derivative. This is a different function. I absolutely need to indicate that. I can't just, if I just bring down the equal sign, I'd be making the statement that these two functions are equal to each other, and they're not. So this is our derivative, and we want to know where is this 0 or undefined. So there's nothing that makes it undefined. So we're just going to be concerned with where is it 0. Now this is a product, so we can find where it's 0 just by setting each of the factors equal to 0. And e to the x is never 0, so we don't get any critical values from that. And 1 plus x is 0 when x equals -1. So this is our critical value. So we've done the first part, find any critical values, and then it says any maxima or minima. So we're looking for a place where, like, a maximum value. If I think about a graph, and I'm not graphing this particular function here, I'm just being really sort of generic. But a graph has a maximum if it does something like this, right? That's this point right there is a maximum. It has a minimum when it does something like that. That point right there is a minimum. And at these spots, this is where the derivative is 0, right? The slope of that tangent line is 0. So finding maxima and minima is all about finding critical values. So this critical value might be a maximum or minimum. We're just not sure yet. It could be neither. So what we're going to do to help us figure that out is make a little sign chart for the derivative. You might remember doing this in Calc 1. And what we do is we make a row for each factor. So a row for e to the x, a row for 1 plus x, and then a row for their product, which is f prime of x. There's only one critical value. Along the bottom here, this horizontal line, that's like the real numbers line. So that's an axis. If I had multiple critical values, I'd have to make sure I put them in order. There's only one critical value, so that's -1. And then all I do is keep track of the signs of each row. E to the x is always positive, so that's easy. 1 plus x is 0 at -1. If I plug in something less than -1, it's negative, and if I plug in something greater than -1, it's positive. And then to get the last row, I'm just going to multiply the two top rows. So to the left of -1, I have a positive times a negative, which means this is a negative. At -1, that's where the derivative is 0, and over on the other side, for values greater than -1. I'm multiplying two positives together, and that's a positive. So what this tells me, if the derivative is negative, that derivative is negative precisely where a function is decreasing, and a derivative is positive where a function is increasing. So what we have going on here is that to the left of -1, my function is decreasing, then that derivative is 0, so it kind of has to level out to get that horizontal tangent line, and then it turns positive, so it's increasing. That means that we have a minimum at when x is -1. Now when we find a minimum value, we want to find not only where it happens, so we know it happens when x is -1, but then we also want to find the y coordinate. So let's find f of -1. Our function is x e to the x, so that's -1 times e to the -1, or -1 over e. And so now we can state our answer. We have a minimum at the point -1, -1 over e. All right. E to the x is its own derivative. That means it's also its own integral. So the integral of e to the x dx is e to the x plus a constant, of course. And the integral of e to the u du is e to the u plus a constant. You might recall that integrating has a lot to do with accounting, making something, see if something fits a form. We can't always make it fit a form, but we could see if it does fit a particular form. So here we have the integral of e to the 3x plus 1 dx. So it's not just e to the x, right? It's e to some stuff, which means if it fits this form of e to the u, we need to see du right there. So in this problem, we're going to make a little u substitution. We're going to say let's let u equal 3x plus 1. And if u is equal to 3x plus 1, then du is 3 dx. So I almost have du. I'm off by this factor of 3. Right? I want a factor of 3 down there. All I have is the dx. I want 3 dx. But I'm allowed to throw in a factor as long as it's just a constant factor. I cannot throw in x's, but I can throw in a constant factor of 3, provided that I compensate with its reciprocal outside. So there's a 1/3. Now, let's see how this shakes out. This right here, that is du, right? That's 3 times dx. This right here is e to the u. So I'm going to rewrite this integral with u's. We got 1/3 integral e to the u du. Now that we've written it with u's, the integral is simple. The integral of e to the u is e to the u plus a constant. And now there's just one step left, which is I got to put the u, that expression for u back in. I got to put the x's back in. So 1/3 e to the 3x plus 1 plus a constant. Okay, let's try another. We're looking at e to the 1 over x divided by x squared dx. So, you know, I'm not entirely sure how this is going to work out, but if this is going to fit an e to the u integral, the only way that's going to happen is if u is equal to 1 over x. So I'm just going to try that over here. I'm going to say let's let u equal 1 over x, which is x to the -1. I'm writing it that way because once I pick u, the next thing I have to do is find du based on this choice of u. So du now is -x to the -2, or -1 over x squared. Oh, I forgot my dx. There we go. All right, so dx is a -1 over x squared dx, and it looks like I kind of almost have that right here, right? What I need is a factor of -1. if I throw in a factor of -1 and then compensate out here, then this part, that is du. And this part up here is e to the u. So rewriting this, we have negative integral e to the u du. Now, again, that's that same integral that we know how to do, right? This integral is simple. Whoops, I'm integrating, so I don't need the integral sign anymore. The integral of negative integral of e to the u is negative e to the u plus c. And now we're going to put the u back in, that the x's. Negative e to the 1 over x. And then plus a constant. Okay. Next, we got one more. We want to integrate 1 plus e to the x all squared dx. Now, before we think about, well, maybe, when you take a look at this, you might have some ideas for what u could equal. And usually somebody will look at this and think, oh, you know what, maybe it's like a power rule, because if u is equal to 1 plus e to the x, then that would be a u squared, and I know how to integrate u squared. It's a power rule. But if u is 1 plus e to the x, du is e to the x dx, and I don't have a factor of e to the x out here, right? I can't add in e to the x. The only factors I'm allowed to add are constant factors. And so that's how I know that this substitution isn't going to work. And if that substitution isn't going to work, then I'm going to use one of the only other options that we have, and it's a good option. It's one that we should always remember that we have, that we can try, and that is some algebra, right? Integrating is often about being clever about how to rewrite a function so that its form kind of reveals itself to us. So let's FOIL this out. Let's expand that square. This is 1 plus 2 e to the x plus e to the x and squared. And so that's 1 plus 2 e to the x plus, if I square e to the x, right, if I'm raising a power to a power, I can multiply those exponents. So that's e to the 2x. And now we can use another property of integrals, which is super convenient, which says I can split up an integral over addition here. So I've written this in this line as one integral, but I can actually just rewrite it as 3 different integrals. So I got the integral of 1 dx plus, and I'm going to do 2 things for this middle integral, okay? I could write that as the integral of 2 e to the x, but you can also pull out constant factors. So I'm going to write this as 2 times the integral of e to the x dx, and then plus the integral of e to the 2x dx. And what is helpful about splitting up this integral is now I get to consider these separately. So the first integral, the integral of 1 dx, we know the integral of 1. The function whose derivative is equal to 1 is just x. And then I have 2 times the integral of e to the x dx. Well, that's e to the x. It is its own derivative. And for the last integral, I've got not just e to the x, but e to the 2x. I've got e to some stuff. And for this one, I'm going to let u equal 2x, so that du is 2 dx. I'm going to throw in a factor of 2 and a factor of 1/2. And this is, I'm going to rewrite the integral first. 1/2 integral e to the u du. And so this is 1/2 e to the u plus a constant. And I'm just going to put the u's back in, or the x's back in. 1/2 e to the 2x. And there's our integral.